If you need new hands, get them at the hand store. So what we've been talking about are equilibrium conditions with forces. We've talked about how if the sum of the forces in the x direction add to 0 and the sum of the forces in the y direction add to 0, we're in a translational equilibrium. We're not speeding up, we're not slowing down, we're just either constantly moving at the same speed, or if we were stationary, we're just holding our position. Okay? But we can be moving here. All this implies is that in every direction, our acceleration is 0. So we're just not speeding up, we're not slowing down. Now, what we're going to do here is we're going to look at a problem where instead of pushing or pulling on something in a straight line, we're going to push or pull at something at an angle. And the reason why this matters is if we think back to what we've done in this class, normally if we have like a box on a table or a surface, whenever we pull on it from one end, let's say we pull on it with 10 newtons. If this is a rough surface underneath, maybe there's like some grass or gravel underneath this here, that's going to bring about a friction. And if our acceleration is 0, we're not speeding up, we're not slowing down, this would imply that the friction, which is fun, is going to be equal to 10 newtons as well, because if this is positive 10 and this is a minus something and our acceleration 0, this better be 10 here, right? Now, everything about this is just standard F equals ma. We know F equals mu n for the friction amounts, and it's what we've been doing. And one of the reasons we were able to do this so easily is because we were able to say, look, this box has a weight, which is equal to mg. We know that. And because it's on a table, it also has a normal force, which happens to equal the weight, which is mg. And we were able to do that to say, look, if this is the normal, I can put the normal down into friction and I can solve some stuff out and da-da-da-da. All sorts of math, right? We've done problems like that. Well, what we're going to do this time is instead of pulling or pushing an object exactly in the same plane as the surface, the ground or the table, what we're going to do this time is we are going to push or pull the object upward. And we're going to see that a lot of things change when we do that. When we push or pull an object upward, what is going to happen is that our friction and our normal force are going to change. Our normal force is going to actually become smaller, and it will no longer equal the weight, or mg. So our normal force will not equal the weight. Okay, it's going to be something smaller in this case. It could be more if we kind of push down into the table, but in this case, it's going to be smaller. But it's just not equal to the weight. Furthermore, this frictional force is not going to be equal to the force that we're applying. So we're applying 10 newtons of force here. Friction won't equal 10. It'll equal something else in this case. And the reason being is because since this 10 newtons here is pulled at an angle, we're going to have to split it up into its x and y components. So our normal force has changed, and since the normal force has changed, our friction will change as well, and it's not equal to the applied force. So that's two things we have to think about here. We are still going to just use our equilibrium equations where we're summing forces in the x and y directions, but as we're starting to see, our free body diagrams are becoming a little bit more complicated. So let's use these two equations, the sum of force in the x direction equaling 0, and the sum of force in the y direction equaling 0, our equilibrium statements, in order to look at this example problem down below. So in this example problem, what we have is a rescue worker, a ski patrolman or woman, pulling an injured skier lying on a toboggan. Now, if you've ever been to a ski resort, maybe it's a nice weekend or something, ski patrol are often on the mountains either doing training or taking dogs out to train them. But if you're unfortunate enough, you will see them rescue people from the mountainside. And they have these like nice bright orange toboggans or like kind of neon toboggans that they lay people on. They're kind of like stretchers, and they will ski with them down the mountainside. And the thing about skiing with someone down a mountainside is you don't want to speed up and you don't want to slow down. You want to keep things a nice, constant speed. Because if you speed up, you start to gain speed, and that can be dangerous for whoever's injured on your stretcher. And if you slow down, that stretcher could slow down at such a way that maybe you lose control of it as well. So you're really trying to keep our velocity constant, which means an acceleration of 0. Okay, so what we're looking at in this problem is a person is on the toboggan with a combined mass of 127 kilograms, and they're being pulled across flat snow at a constant speed. So a constant speed implies that our acceleration is 0, which means that all of our equilibrium conditions can be applied here. A rope is attached to the toboggan at ground level, and then the rescuer holds it over their shoulder, and we're going to make a 43-degree angle due to that, based off of these heights here. But the other key thing is that the tension in the rope is 148 newtons. What we are looking for is what is the coefficient of friction between the toboggan and the snow. So we are looking for in this problem mu. Okay? So let's tackle this just like great physicists do. First, we recognize that we failed out of our art school, and we are going to draw a picture anyways. So here is our beautiful picture. Toboggan. Person who's unfortunately broken. This was almost me once. I fell really bad skiing, and I totally tore my labrum in my shoulder. Ugh, bad time. Skiing is super dangerous. And then there's a rope attached to the toboggan. And this rope goes over a person's shoulder. Here's our ski patrol. They look like a zombie for some reason. And we know that the angle that this is made is 43 degrees here. And we know that the tension in the rope is 148 newtons. We also know that there's going to be some friction back here. And we'll take care of that in our free body diagram. So that's our actual picture right there of the problem. Let's make a free body diagram now instead of just dealing with this picture, because this is kind of like complicated to look at. So here's our pick. Let's look at our free body diagram. So if we have the free body diagram of our person, our person is laying there in the sled, and they have a weight, which is mg, and their mass here was 127 kilos, and that's going to be multiplied eventually by 9.8. Okay. We know that there is a tension acting at an angle like this. So that's 148 newtons. And we know there is some friction opposing the motion of the sled, so the friction's acting backwards here. We know friction's fun, so let's just put in a mu n. And we also know there's going to be a normal force. And this normal force is not going to be as much as the weight, because we're actually lifting the sled a little bit off the ground. So this normal force will exist. Okay? So that's what we have here. That's our nice free body diagram listing everything. Maybe one of the things that we've noticed is that this tension, since it's at an angle, we're going to have to break it up. So if here's the sledder again, and there's the tension of 148, we could recognize that this tension can be broken up into a X amount of the tension and a Y amount of the tension, with that angle on this triangle being 43 degrees. So we can break this up into its X and Y's. We might as well do that right now. If we take a look at this using the magic of SOHCAHTOA, then what we're going to see here is that our adjacent side is tx, which means we're using cosine on it. So we can say that this is 148 times the cosine of 43 degrees. And if we calculadora that, 148 times the cosine of 43, oops, use the right buttons, we get 108.24 newtons. And if we do this for ty, this is our opposite side here, and using the hypotenuse, that'll be a sine term. So this will be 148 multiplied by the sine of 43. So 148 times the sine of 43 degrees gives us 100 point, what is that? 94 newtons. Okay. And at this point, we know a lot about our setup. So let's go ahead and apply our equilibrium conditions. We know the sum of the forces in the x direction are going to add up to 0, and we know the sum of forces in the y direction are likewise going to add up to 0 because our person's not speeding up or slowing down. They're maintaining the same speed. So choosing directions to be positive or negative, classically, we choose right to be positive and left to be negative, up to be positive and down to be negative. But like I always say, if you want to switch, you're more than welcome to. It doesn't matter. It'll all work out in the end. And if we run our x direction here, we'll find that we have Tx, the tension in the x direction, which is positive, it's pointing to the right, minus some friction equals 0. And if we wanted to put in some numbers here, we could, say that this is like 108.24 minus, well, friction is fun, so we can put in mu and we can put in n, and that's going to be 0. But I don't know what mu is, that's what we're looking for. And I don't know what the normal force is right now, so this is kind of stuck. Ugh, hate getting stuck. If we're stuck, let's just keep going. Let's try things in the y direction. We actually have 3 forces in the y direction. We've got the tension in the y direction acting up. We've got the normal force, and we have the weight. So there's 3 things there. So we've got Ty plus a normal force minus a weight equals 0. And if we throw some numbers in for all of this, we're going to have, what is that, 100.94 plus the normal force minus the weight, which we could actually grab that number. It's 127 times 9.8. What is that? 1244.6. Ooh, that's a big number. 1244.6. And that's going to equal 0. Well, this is actually kind of nice here because these numbers in the y direction, they're like terms. Everything is a newton down here. They're all forces. So I can combine them and I can solve for the normal force. And when I solve for it, I can put it back up here, and then I can solve for the coefficient of friction. So let's solve for the normal force real quick by combining these numbers. 100.94 minus 1244.6 gives me normal force minus 1143.66 equals 0. And this pretty clearly means that our normal force has to equal 1143.66. We just bring it to the other side. I'll just put the equal sign there. So this is indeed our normal force. We can take this value and plug it back up here. So if we continue our x direction again, we have 108.24 newtons minus mu times 1143.66 equals 0. And at this point, we just have to solve this math. This math is actually pretty straightforward for us to solve. You can solve it at this point any way you really want. You can either bring the 108.24 over to the other side, so you'd have something like, how would that look? You'd have something like negative mu 1143.66 equals negative 108.24, which you'd see there that the negatives divide out. Or if you wanted to, you could move this entire term over to the other side, in which case you'd have something that looks like 108.24 equals mu times 1143.66. Notice that in either case, it doesn't matter. We get the same thing. We need to get mu by itself, though, so we'll divide by the 1143.66. That divides out 1143.66. Remember, our units for both of these are in newtons, but newtons over newtons, they divide out, they cancel each other out, which is nice because the coefficient of friction is a unitless quantity, or it's force per force, of course, said the horse. But we're basically there. So 108.24 divided by 1143.66 is 0.095 newtons per newtons, or a unitless quantity. And that's our coefficient of friction here. That's what we're looking for in this problem. That's how much frictional kind of a feel that the sled has to the snow. So it's a kind of cool thing that we're looking at there. But once again, for these kind of equilibrium problems, we see that we've drawn a picture. Nothing new there. Thank you, Grandpappy Botzer. We set up our free body diagram. Since one of our forces, the tension here, is at an angle, we simply said, hey, let's break it up into sine and cosines, x's and y's. Okay, we did that. Nothing too crazy. We then sum up all of our x's. We summed up all of our y's, and then we played some math in order to get everything that was missing until we got our final answer there. Okay? So with that, this one is finished. Hope you enjoyed it. So adios and take it easy.